Yeah, so good evening, everyone. So this is week second discussion of this course, Social Network, and this course is taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering, IIT Roper. Myself, Ayan Paul. I am the I am a PMRF research scholar from IIT Kharagpur, and I am a TA of this course. By TA, I will discuss with you some of the question that will be very similar to your assignment question. So whenever you will do your assignment question, you will not feel it's completely new. Okay, so that is how I will operate. But before that, I always prefer to just discuss few theories and concept related to the week, so that whenever we will be doing our questions, it will be easier for us. Okay, so by this, let's start. So the discussion of this week is dataset, that is social network dataset. Okay, so what are this dataset? Social network dataset are structured collection of nodes. Everyone knows what is nodes: user or entities, and edges, that is relationship and interaction used to study behavior, influence, and community dynamics. Okay, so that are datasets. So what are the types of datasets that has been discussed with the okay, someone is yeah. So people are still joining, so that is why I have to interrupt in between. So yeah, so ingredient network, that is the first network that has been discussed in this week. That is, what is an ingredient network? It is a type of graph model used to represent relationship between the ingredients. Yeah, ingredient, what are the ingredients? The ingredients that are used typically in food, right? That typically in the context of recipes, food science, and flavor analysis. So in this, what will be the nodes will be ingredients. So any network, our first step is to identify these two things: one, what are the nodes, and second, what are the edges. Okay, so nodes here in this ingredient networks are ingredients. Okay, and edges will be a relationship between the two ingredients. So this is regarding ingredient networks, such as co-occurrence in the same recipe, flavor compatibility, or the chemical similarity. By this, the ingredients will link with each other. So by that, our first network will be formed, that is known as ingredient network. Okay. So again, I am repeating: ingredient network, type of graph model used to represent relationship between ingredient, typically used in context of the any food, like recipes, food science, flavor analysis, etc. Okay, so in this, what we have to identify in any network: what are the nodes, what are the links, or links or edges, whatever. So nodes here are ingredients, edges that are relationship between the two ingredients. How? The relationship will be based on the co-occurrence in the same recipe, or the flavor compatibility, or the chemical similarity. Okay, so that is our first network, that is the ingredient network. Okay, so these are the ingredient network, whatever you are eating. So by this, whatever ingredient will have, we will just form a network in between them, and you can see one of the ingredient network shown over here. Okay, so this is a ingredient network. The second network that has been discussed in this week is synonymy network. So what is a synonymy network? Is a graph based representation of words, where nodes will be words and edges will be synonym relationship between the words. That means words which are synonymous to each other, they will link. So that is synonymy network. So in simple term, in models, how words are connected through similarity in the meaning. For example, you can see the faith is connected to belief. For example, anger is connected to hate. Apple is connected to fruit. Similarly, like that. So that is synonymy network. Third, we have this web graph. Web graph, it is a very common type of network. Everything that you are using in internet is based on this web graph. So a web graph is a uh, is a graph representation of world wide web, that is www. You know, every time you are visiting a site, you are typing www, that is the world wide web. So okay, someone is, yeah, so that is a world wide web. So world wide web is based on this web graph. So web graph is a graph representation of this world wide web. Nodes will be the web pages. Edges will be the hyperlink from one page to another page. In simple term, it models how web pages are connected via the hyperlinks. That is the web graph. So this is the thing. So now the question is from where we can download some of the sites, some of the social media dataset. So popular website, you have the Snap, that is very popular, Stanford Network Analysis project. You can search after this class. You can search. So purpose, real world social web citation network, etc. You can find Kaggle. It is very popular these days. So data science competition datasets. Social media graphs, interaction data you can get. Network repository, large graph dataset archive, social, biological, and infrastructure networks you can get. UCIML repository, this is also old repository, but old website where you can get this social media datasets. So here you can get this academic datasets. Clean network dataset, that is a feature of this. Jeffy dataset, sample network files, visualization, ready graph data, and last we have this pagerank dataset, pagerank graph collection, large scale networks. So this is a table I have just given you. So you have seen a what called pagerank. Okay, so what is this pagerank? So dataset can be of different formats. Okay, one format is the pagerank. The most simpler format is CSV, that is comma separated values. So CSV file you must have seen again and again. So it is very similar to your Excel file, only it is separated, the data is separated by comma. Excel you have this columns, row, etc. But data is separated by cells. Here data is separated by comma. So that is the .csv format. File extension is .csv. Okay. So significance, simpler tabular format, easy to load. You can operate your Python codes very easily on this. Excel, R also you can operate through this CSV. Commonly used for edge list and note attributes. Where to download? These are the sites you can download. Then you have this GML, graph modeling language. The file extension is .gml. So structured text format, it supports the nodes, nodes, edges, attributes widely used in NetworkX and Jeffrey. So this is the second format, graph modeling language, .gml. Okay, .gml. So the problem with this CSV is it will not have this attributes. Okay, but here it will have this, it can have this attributes of nodes, links, etc. So that is the second format. Third format which is very popular in case of this social network dataset is pagerank network format or .NET extension. So efficient for large networks, used in pagerank software, compact representation. So this is the thing. Then we have this GraphML. This is again a popular graph markup language, XML based. So everyone know XML file, right? So this GraphML will be very similar to your XML file only. So high structure extensible support. Snap network repository supports metadata, interpolates across the tools. So this is the fourth format. And then you have with this GEXF format, graph exchange XML format, GEXF. So designed for dynamic evolving network, native format of Jeffrey. So for more details, you can see your this lecture video where it has been shown how the datasets are seen, etc. You can see, you can refer to your lecture videos. Okay. So in this short time it cannot be discussed or just shown, but you can just follow your this lecture video. There is a very good class in which they have just show you how the data are visualized. Okay, so this is the thing regarding the social media dataset. Okay. Okay, and then you have what are the use cases. Okay. Okay, what are the use cases? What are the best formats? You can ask me that there are so many formats. So which format is the best format? So if I say you are beginner analysis, Excel, you are working with Excel or Python Pandas. Pandas is a Python library, okay, where you can just visualize the datasets. So that is Pandas, okay. So you can use the CSV format. When you are operating in NetworkX, this GML or GraphML format is good. And then very large network, when you are dealing, you should go with pagerank. And dynamic network and visualization, where you have to go with this graph exchange XML format. So these are the different type of data sets, and uh, what are the best formats where you can use. And also I have given you this, so where you can download this data set also I have given you. So just you can just check the internet after this and you can download some of the data sets. So now when we have downloaded the dataset, the question is what we will do after downloading the dataset. Okay, people are still joining. Yeah. So what you will do after downloading the dataset? That should be the question to answer. So first, what you have to do? Steps in social. You have to do the for social network analysis. First step is load the dataset. Once you have downloaded all this dataset from this, what you have to do is you have to load the dataset. Second, you have to build the graph model, and step 3, you have to compute the network measure like degree, centrality, or clustering, or part based measure, etc. Okay, so that is how we do the analysis of social network datasets. So again I am repeating. So basically there are 3 steps. Okay, first step is load the dataset. All this dataset you can just go with any this repositories, you can just visit it, you can download the dataset. After downloading the dataset, first step is to load the dataset. Second step is to build the graph model. Okay, how you can build a graph model? Very simple. You know network X, we have discussed in the previous class. So just okay, someone is joining. Yeah. So after loading the dataset, you have to build the graph model. Once you build the graph model, you have to compute the network measures. Okay, so let's see what are the network measures. First is degree. That is very you can say very common and very much used. So what is degree? Number of direct connection the node has. Okay, so that is degree. A number of direct connection that the node has, so that is degree. So you will ask that every node will have different degree. So yeah, every node will have different degree. We measure degree for a certain node. So if we want average node, what we have to do? We have to calculate degree of each and every node and then divide it by number of nodes. That is to get the mean or average degree of the network. So that is degree. So again I am repeating, degree centrality, this is the most common. Number of direct connection a node has. So if I consider a node V, a number of edges connected to this node V is known as the degree of the V. Okay, so that is the first measure, that is degree centrality. Okay, so meaning high degree, that we can say it is a popular or well connected user. Okay, so that is degree centrality. This is the Python code by which you can get the degree centrality. Okay, so this is actually this G is nothing but your graph. Okay, and G dot degree, by getting by just printing G dot degree, you can get the degree of the network. Okay, so this is the thing. Now this degree is generally used for undirected graphs. Okay, undirected graphs means both way graphs, right? Means it does not have any direction. But in case of directed graphs, we use this tool, that is in degree and out degree. Because directed graph, you will have a certain direction like this and this. Okay, so your link is going from, let's say this is A and this is B. Okay, so your link is going from A to B. So B will have this in degree, A will have this out degree. Okay, so that is why two type of degree, in degree as well as out degree. Again, it is very simple code, G dot in degree and G dot out degree. By this you can get the in and out degree of a directed network. Okay, so this is regarding degree. And then you have this centrality measures. So there are different centrality measures. So most common is this betweenness centrality. Okay, so betweenness centrality, shortest path through it measures the bridge importance. Okay, so shortest part, that is sigma. Sigma means addition of all the terms. So sigma shortest path through V divided by all shortest path, that you have to do for all the nodes. That is V equals to 1 to n if there are n nodes. So by that you can get the betweenness centrality. If the betweenness centrality is high, connector between communities is nothing but clusters, right? The clusters. So if the betweenness similarity is more, then we can say this clusters are connected. All the clusters are very much connected to each other. So that is betweenness centrality. Then you have this closeness centrality. Okay, measures how fast a node can reach others. Okay, that is closeness centrality. High, that is fast information spreader. Then you have another centrality known as this eigenvector centrality. So measures importance based on the important neighbors. So again, codes are very simple, like nx dot betweenness centrality, nx dot closeness centrality, and nx dot eigenvector centrality. By this you can get the all these things. So it influences so it influences in influential circle. Okay, so eigenvector centrality, where it has been used, it measures the importance based on the important neighbors. So that is eigenvector centrality. And then we have something called pagerank, that is used for directed networks. So what is this pagerank? Meaning influence in webs and citation networks. Okay, so pagerank, it generally consist of two things. That is how much a node is connected to other nodes, and second, how much this node is connected to important nodes. So this two measures it measure. Okay, so that is page rank. And then you have this cluster coefficient, that is number of links between the neighbor divided by maximum possible links. Okay, so that is this clustering coefficient. And then you have this path based measure, like shortest path, average path, and diameter of the network, that can be found out by very simple formulas, like nx dot shortest path, nx dot average shortest path, then nx dot diameter of the network. So that is how we can do the analysis of the social network data set. Okay, so this is again a very important topic. So what I have told, there are different social network dataset, and then we can download this dataset in different formats. Once you download the dataset, you can load the dataset, build the graph model, and then compute the network measures like degree, centralities, clustering, path based measures, etc. Okay, so this is regarding this analysis of social network data sets. Okay, so code also, I have given a code also, so you can just check in that folder. Okay, so yeah, let me give you the links first. Okay, so just 1 minute. Yeah. So I think you all know this link, but still I am again giving you in case you just missed it. Just 1 minute. Yeah, so this is the link of your drive link, where I am uploading all the week literature as well as codes. Okay, so you can just visit this. Also, you can just open this video. Just let me, yeah, this is the video of the previous class, so you can just see, you can just watch this video in case anyone missed the previous class. Okay, and in this video only you can get the channel link, so you can just subscribe the channel if you want, so you can get all the videos. So every week I will be, whatever we are discussing, I will be I will be recording this video, and I will upload in that YouTube channel. Okay, so this is regarding this two important links that I have given you. Okay, so just follow this two links. So, and if you don't want to follow this two links, there is another link called the master link. So just let me see. Yeah, this spreadsheet link. So this also I am giving you. This is the third link, that is the master link. So this is a spreadsheet link wherever you will get all these things, like this drive link as well as the week wise videos. Okay, so these are the three links you should always remember. Okay, so this is regarding this. So let us again move on to the discussion. Okay, so our last topic is emergence of connectedness in social networks. Okay, so what is this emergence of connectedness? So in social networks, emergence of connectedness refers to a sudden formation of large connected component called as giant component, as nodes and edges are gradually added to the network. So social network is a dynamic platform, so nodes and edges gets updated with passing time, right? So this phenomenon, where sudden formation of a large connected component called as giant component emerges as nodes and edges are gradually added to the network, that is known as emergence of connectedness. Okay, so emergence means emergence, that is the common English one, and connectedness. Okay, so that is emergence of connectedness. Initially, network consists of small isolated clusters, but beyond the critical threshold, a large fraction of nodes become interconnected. So initially there will be any network, when it is formed, initially communities or the clusters will get formed, right? And there is less betweenness, centrality in between the community. But after a certain threshold, what it will happen is it will become a large community, because will be more betweenness, centrality in between, and nodes will connect in between community or in between cluster. So by that, what will happen is this is small isolated cluster will become a large fraction of interconnected nodes. Okay, leading to rapid connectivity growth. So that is known as emergence of connectedness. So this phenomena is a phase transition similar to physical system, and is widely studied using random graph theory and percolation models. Okay, so concept of connected components. A connected component is a graph. In a graph is a maximal set of nodes such that a path exists between every pair of nodes in that set. Okay, so that is connected component, connected graph, right? That we have discussed. There are two type of graph: unconnected graph and connected graph. Though there are more possibility of connected graph. We have seen in the previous class also, like 25 nodes over this community and 25 nodes over this community. So the chances of connectedness of this cluster with this cluster is like here, if there are 25 friends, and if there are 25 friends, though the chances of connectedness is 25 into 25, that is 625. So there are 625 possibilities by which this cluster will get connected with this clusters and form a connected graph. Otherwise, this is an unconnected graph, right? Because there is no link between this community and this community, or this cluster and this cluster. Okay, so this is the thing. So again, concept of connected component. A connected component is a graph. In a graph is a maximal set of nodes such that path exists between every pair of nodes in that set. Okay, so if there will be a connection anywhere, and there will be a connection with any node of this community to any node of this community. Okay, so that is known as this concept of connected components. So small components, isolated groups; giant components, component containing O and N, that is complexity. So complexity N nodes, a finite fraction of the total nodes. Okay, so emergence phenomena. Low edge density, many small disconnected component. Near a critical threshold, sudden formation of giant connected component. Above this threshold, network becomes largely connected. So 3 stages. First, there will be a low edge density, many small disconnected components, or this components cluster community, whatever, these are synonyms. Okay, so small disconnected components or clusters will be there. Near a critical threshold, sudden formation of giant connected component, and after above this threshold, network becomes largely connected. So this sudden transition is called as emergence of connectedness. Okay, so this is the theory. And then there are graph model. This is a graph model called as Erdos Renyi ER model. Okay, yeah, Erdos Renyi ER model. So n here is the number of nodes, p here is the probability of an edge between two nodes. Okay, so we write this graph as g n p. There are two attributes, n that is number of nodes, p is the probability of an edge between the two nodes. So average degree that we can get, that is p into n minus 1. So that is the average degree that we can get. Critical threshold for this giant component, a giant connected component emerges when this k, okay, will be equal to 1. In that case, there is a giant component will emerge, that is pc, that is the critical threshold, that critical threshold probability, that will be 1 by n. Okay, so these are all mathematics, but what is important is this table. So average degree will be k. If k is less than 1, then small isolated cluster, k very close to 1, phase transition, and k greater than 1, giant connected component. So this is the mathematics of this Erdos Renyi random graph model, or the ER model. Okay, two attributes, n and p. N is the number of nodes, p is the probability of an edge between the two nodes. Okay, so this is by this we can get the average degree. Once we get the average degree, we have to see this. If k is less than 1, k that is approximately equal to 1, or k is greater than 1. If k is less than 1, then small isolated cluster, k is approximately equal to 1, that is close to 1, that is phase transition is happening, k greater than 1, giant component is forming, that is emergence of connectedness is happening. And then there is this phase transition in networks, small parameter change, large structural change. Okay, so that is phase transition network. The emergence of connectedness is an example of phase transition. This is the phase transition, small parameter change, large structural change. Okay, so that is the phase transition network. By small parameter change, we can get a large structural change. For example, k very close to 1, what will happen is k you will just small you will make just small parameter change to make k just greater than 1, and there will be large structural change. Okay, similar to water, to ice, magnetize, just forget this. Then percolation theory, this process is also explained using percolation theory, where nodes or edges are gradually added at critical occupation probability. Global connectivity suddenly appears. Okay, so there will be side percolation, nodes added gradually, bond percolation, edges added gradually. Okay, so this is the percolation theory. Okay, so this process again I am explaining. So this process is explained using percolation process. Which process? That is emergence of connectedness. Okay, here nodes or edges are gradually added. Either nodes will be added or edges will be added. When nodes are added, this is known as side percolation. When edges are added, this is known as bond percolation. Okay, at critical occupational probability, this is the probability, global connectivity suddenly appears. Okay, so this is this percolation theory. And then there is growth of giant component. Okay, let s be the fraction of nodes in the giant component, then s equals to this. Okay, this equation models the giant component size, so no need to discuss this, but just keep in mind factors affecting the emergence of connectedness. Average degree, that is important, most critical. Number of nodes, larger, sharper transition. Okay, edge formation probability, control the phase change. Network topology, random, scale free, or the small world. So these are different type of network we have discussed. There can be random network, there can be small world network. This is, I think, scale free, and any other type of network. So this is how these are the factor affecting the emergence of connectedness. So most important factor is this average degree. Okay, and then you will have number of nodes, the edges formation probability, and at last how is the network topology. Okay, so example of the emergence of connectedness in the social network: social media, viral content spread, mobile messaging app, sudden mass adoption, epidemics, outbreak after threshold, hashtag trends, sudden popularity, power grid, cascading failure. So these are some real examples of this emergence of connectedness in social networks. Okay. So this is the theory that we have discussed. So topics on which, okay, just okay. So topics on which week 2 assignment question are based, it is based on social network dataset, social network dataset types, that is ingredient networks, synonymy network, or this web graph, then social network dataset analysis, and at last emergence of connectedness. Okay, so is the theory clear, or at least you get something? I hope you have just gone through all your lecture videos, and this is a brief summary that I have discussed, whatever that has been discussed in your lecture videos. Okay, so I hope this is clear. Can we move to the question parts? Okay, so just 1 minute. So this is the first case or first case study. So first case study is about the ingredient network. In a large culinary database, each recipe is represented as a set of ingredients. If two ingredients often co-occur in recipes, example salt and pepper, they are connected in the ingredient network. And over time, chefs started noticing that some ingredient like garlic, onion, and olive oil frequently appear with many others. Okay, forming a sort of central hub. Okay, a data analyst wants to model this network to identify how ingredient pairing influence the recipe innovation. Okay, so this is the first case. So theory required for this case one, that is the ingredient network. Basic of graph representation, like what is a graph, in graph and what is nodes, but this is in this ingredient network, nodes will be ingredient, edges will be co-occurrences in the recipes. Type of graphs, there will be undirected graphs since co-occurrence is mutual. Unweighted graph, simple presence absence of co-occurrence. Okay, so generally it will be undirected graph only since co-occurrence is mutual. And core concept, node, edges, degree, path, connected components, cluster, community, etc. Okay, and then central measure, yeah, there are this three important centrality that is that should be discussed. One is this degree centrality, number of direct connections, identifies popular hub ingredient. Between the centrality, measures how often a node lies on the shortest path, identify the bridge ingredient connecting cluster. And last, closeness centrality, it measures how fast a node can reach others, helps understand network readability. Then we have this third, that is clustering coefficient and local density. Clustering coefficient, how connected a node's neighbor are, meaning high clustering, it is tight groups, similar cuisines, and local ingredient groups. Okay, so this is the third concept. Fourth concept, community detection and network clustering. What is a community cluster in a network? Okay, algorithm or idea of community detection. Why clustering helps: finding substitute ingredients, identifying ingredient groups by cuisine or function. So this is the community detection and network clustering. For example, if we can see for a pizza, there are certain common ingredients that are common with cheese, and if we can trace this community, we can see with cheese what are the ingredients that goes well. So that cheese, if we are using in other food, we can easily say that we can test with this other this ingredients that are common in common in pizza. Okay. So that is why community detection and network clustering is important. And then you have this small world network theory. What is a small world network? High clustering, short average path, real world example, social network, food ingredient network, and word network. Okay, so small world network means there will be cluster and there will be a large betweenness similarity. Small cluster, but there will be high betweenness similarity. That is small world network. So structural node of rows of nodes, hub, that is high degree node, bridge, high betweenness node, cluster member, high clustering coefficient, community, dense group of nodes. Okay, so that is the theory you should know. And with that, let's discuss the question one by one. Which of the following? Okay, people are joining. Okay. So, which of the following could be used as an indicator of central ingredient with the in the ingredient network? Okay. So, high degree centrality, low clustering coefficient, high betweenness centrality, and minimum spanning tree membership. Indicator of central ingredient in the ingredient network. Yeah, high degree centrality will be there, and I think low clustering coefficient. Okay. Sorry, high betweenness center. Okay, so which of the following could be used as an indicator of the central ingredient? Okay, in the ingredient network. So high degree centrality and high betweenness centrality. So high degree centrality, it indicates the ingredient co-occur with many others. That is high degree centrality. Example, garlic appears in many recipe with the different ingredient, making it as a hub. Okay, and high betweenness centrality, it captures the ingredient that lie on many shortest path between the others, meaning they connect different ingredients group. Example, olive oil, bridging Mediterranean and fusion recipe. Low clustering coefficient, it does not imply certainty. Very true. It just means neighbors are not well connected. Okay. Minimum spanning tree membership is not a meaningful indicator for importance in the real world ingredient network. So A as well as C is your correct answer. Okay. Okay. So let's move on to the next question. If the network is unweighted and undirected, which metric would best indicate an ingredient connect? Okay. Okay, just give me 5 minutes. Okay. Okay. Sorry for disturbance. Someone was on the gate. Okay. So let's again move on to the discussion. Yeah. So so if the network is unweighted and undirected, which metric would best indicate an ingredient that connects various ingredient cluster? Whether it is degree centrality, betweenness centrality, page rank, or this closeness centrality. So what will be the answer? If the network is unweighted and undirected, okay, which metric would best indicate an ingredient that connected various ingredient clusters? Okay, various ingredient clusters, this is important. That means cluster will be there, and this node node or ingredient will connect various ingredient clusters. So that means degree centrality is not, but betweenness centrality is of highest measure. That is option B will be correct. Betweenness centrality, right? Betweenness centrality. So just, yeah. Yeah, so betweenness centrality, it identifies that ingredient that act as bridge between the other separate ingredients. Example, soy sauce linking Asian and the food cuisines. Degree only counts connection, not whether those connection link distant cluster. Page rank favors popularity, not structural bridging, and closeness measure average distance, not inter-cluster connectivity. Okay, so option B is the correct answer. That is betweenness centrality. Okay, so this is the second answer. Second question answer. Okay, so if the network is unweighted and undirected, which metric would best indicate an ingredient that connects various ingredient cluster? That is betweenness centrality. Okay, so this is the answer of question number 2. Let's move on to the question number 3. So which of the following actions might increase the clustering coefficient of node representing a ingredient? Adding edges among its neighbor, using it in recipes that already share many ingredients, decreasing its degree, or D, connecting to an isolated node. So any guesses for this? Which of the following action might increase the clustering coefficient? So we have to increase the clustering coefficient of a node representing an ingredient. So any guesses for this? Okay, no guesses. So yeah, A as well as B. That is adding edges among its neighbor, using it in recipes that already share many ingredients. Okay, like this clustering coefficient, it measures how interconnected an ingredient neighbors are. This is the definition of the clustering coefficient. So adding edges among neighbors directly increase the triangular formation. Triangular formation means nothing but three nodes, they are connected to each other like this. Okay, so that is triangular formation. So using an ingredient in recipe where other ingredients already co-occur, strengthening the local density. Okay, so using an ingredient in the recipe that where other ingredients already co-occur, strengthen the local density. So by that also the clustering coefficient will increase. But decreasing its degree does not inherently increase the clustering, definitely. So decreasing degree will decrease the clustering, right? Connecting to an isolated node, it reduces the local interconnectedness. Okay, so connecting to an isolated node, it reduces local interconnectedness, so your clustering coefficient will again decrease. So option A as well as option B is the correct answer. Okay. Now let's move on to the next question. What is the best way to identify a substitute ingredient in the network? Using pagerank, using community detection to find cluster of similar use ingredient, finding the node with maximum degree, running BFS from each node. So any guesses for this? What is the best way to identify substitute ingredient in the network? Using community detection to find cluster of similar use ingredient, that will be the correct answer. Okay, so explanation, substitute ingredients tends to appear in similar recipe and context. Community detection group ingredients based on shared usage patterns. Page rank and degree identify popularity, not the substantiality. Okay, so here we have to see the substitute. Okay, so we have to see it for the substantiality. So page rank and degree, it will give page rank and degree, it identifies the popularity, not substantiality. And then BFS only explore reachability, not the functional similarity. So option B is the correct answer. So let's move on to the next question. Okay, someone is joining. So ingredients with high clustering coefficients are likely appear in tightly knit groups recipes, uh, be used rarely, be part of cultural or cuisine specific subgroups, form bridges between the disparate recipes. So any guesses for this? Ingredients with high clustering coefficient are likely to appear in tightly knit groups of recipes. That will be right. Be rarely used. We cannot say that. Be part of cultural or cuisine specific subgroups can be form bridges between the disparate recipes. So we cannot say this. Form bridges, that we cannot say this because here is high clustering coefficient. So we are talking about the clusters, not the betweenness. Okay. So yeah, appear in tightly knit group of recipes, that is true, and be a part of cultural or cuisine specific subgroup. Okay. So high clustering means an ingredient appears with a set of ingredients that also frequently appear together. This is typical of regional or cuisine specific ingredients. Okay. So example, garam masala in this Indian cuisine. They are not necessarily rare. Bridges between disparate recipe usually have low clustering and high betweenness. That I have told you. Okay. So option A as well as option C is the right answer. And then last question of this case, that is question number 6. The network of ingredient is most similar in structure to which type of network? Tree, star, small world network, linear chain. Network of ingredients is most similar to structure to which type of network? So that is very easy. That is small world network. Okay, so ingredient network exhibit high clustering. Ingredient form recipe based group. Short path lengths. Common ingredient like salt connects distant groups. So this matches property of the small world network, not tree, star, or the linear chain. So we can say option C is the correct answer for this. Okay, so this is the question number 6. Now let's move on to our case second, that is the synonymy network. A team of linguists construct a network where each node is a word and edges connect words that are synonyms. Okay. They analyze how meaning evolved over time and find that certain verbs like big, good, or fast have dozens of connection, while niche terms like gargantuan, and or stellar sit on the periphery. Okay. So let's see what are the theories required for this graph modeling of language. Okay. So how language can be modeled as graph? Nodes will be words, edges will be synonym relationship. Graph type undirected graph, synonym is mutual. Unweighted graph, simple presence, absence of synonym relationship. Okay. And then required concept, node, edges, degree, path, component, same thing in every question, every cases. Degree and centrality, yeah, number of synonyms a word has. Identify how words like good, big, fast, etc. Between the centrality measures how often a node lies on the shortest path. Identify bridge words connecting different semantic groups. And then general centrality concept, meaning of central versus peripheral nodes. And then we have this community detection and semantic clustering. What is community detection, you should know. And then how it groups semantically similar words, synonym clusters. Okay. And then community detection is nothing but forming some word that are forming clusters. Okay, like good will can have different synonyms, like now you can say good, nice, like that. So it can form a community. So that is community detection. And then peripheral nodes, importance of low degree nodes. Okay. Semantic richness, specialized vocabulary, or context specific words. And then you have this structural rules in network: hub, high degree; peripheral nodes, low degree; bridge, high betweenness; and community member, dense local connectivity. Okay. So these are the structural rules in network. And then you have this sociolect and subgraph analysis. What are sociolect? Formal languages, informal slang languages. Okay. So subgraph based clustering, how formality informality leads to local clusters, right? So if we are talking about formals, so for formal words we will have one cluster, and informal words will form another cluster. So this is another thing. And clustering coefficient, relationship between word usage and local grouping. Okay, so these are the few things you should know to answer the question. Okay, so let's directly move on to the question. Someone is joining. Yeah, so what graph property makes a word like good a hub? High degree, high centrality, low clustering coefficient, high eigenvector fall off. So this is very easy, right? What graph property makes a word like good a hub? Yeah, high centrality should be there, okay, and high degree should be there. Both should be there. So option A as well as option B. So high degree and high centrality, specifically degree centrality, sometimes closeness or eigenvector centrality. Okay. So degree centrality, it counts how many direct connection a node has. A hub like good as has many synonyms, so high degree centrality directly identifies it as a hub. And then you have this high centrality is a broader term. Nodes that are structurally important in the network like hubs often have high centrality measures, especially degree centrality. Other centrality measures like eigen centrality can also indicate hubs if the node is connected to other important nodes. Okay, so low clustering coefficient is not reliable indicator of hub status. High eigenvalue fall off is not a standard metric. So in short, hub is highly connected, high degree, and structurally central, that is high centrality. So both are valid over here. Okay, so option A as well as option B. Okay, so this is a very easy question but very important question. So what graph property makes a word like good a hub? Okay, so that will be high centrality as well as high degree. Okay, so both are true over here. Now let's move on to the next questions. Already okay, so there is some mistake in animation. So what type of network model is most appropriate for modeling the synonymy network? Okay, so option A is tree, option B undirected unweighted graph, option C directed weighted graph, and option D bipartite graph. Okay, what type of network model is most appropriate for modeling the synonymy network? So synonyms means if like if like any word is synonym to any other word, so that means these two words can form undirected graph. Okay, not directed need not necessary, but undirected should be there, right? Like if I connect a tree to the plant, so plant should be also connected to a tree. Okay, so something like that. Okay, so synonym is typically a mutual. Okay, if A is the synonym of B, then B should also be synonym of A. So that means the graph should always be directed graph, not a undirected graph. Okay, tree synonym relationship are not hierarchical. Wherever the relationship is hierarchical, so there we go for the tree. Directed weighted graph, direction and weights are unnecessary unless modeling usage frequency. And then you have this bipartite graph. All nodes are words of the same type, so that is also not required. So option B is the correct answer. Very simple question but very important question. The synonymy network will be undirected unweighted graph. Okay, so this is a important question. Then what why might peripheral nodes in synonym network network be important? They add richness to the to language use. They might connect rarely used synonyms group. They have highest centrality and they always form the cycles. So again I am repeating, why might peripheral nodes in the synonym network be important? They add richness to the language use. They might connect rarely used synonyms group. They have high centrality, and option D, they always form the cycles. So any guesses for this? Okay. So they add richness to the language use, that will be might peripheral nodes and the yeah, they add richness to the language use, that is true. They might connect rarely use synonym groups, that is also true. They have higher centrality, that is false, because peripheral nodes always at the periphery, not the central. So they have higher centrality, that is not true. They always form cycles, we cannot say anything about cycles. Okay, so option A as well as option B is the correct answer for this. They add richness to the language use, they might connect rarely use synonym group. So peripheral words carry specific nuance, tone or stylistic meaning. Okay, some may act as bridge between the specialized or domain specific vocabularies. Okay, so they do not have high centrality. Definitely peripheral nodes do not necessarily form cycles. So these two are false. So option A as well as option B is the correct answer. So let's move on to the next question. What kind of analysis can help group together words with similar meaning? DFS traversal, community detection, shortest path algorithm, bipartite projection. So this is, I think, easy. That is community detection, right? Yeah, community detection will be your right answer. Okay, so community detection, it identifies the cluster of densely connected node which naturally correspond to semantic similarity groups. Example: size, word, speeds, etc. DFS only explores connectivity. Shortest path finds distances, not group, and bipartite projection is irrelevant with two node types. Okay, so option B is the correct answer. In the synonymy network, a node with low degree but high betweenness might indicate a bridge between the two different clusters. A context specific synonym, a very frequent word, an isolated component. In the synonym network, a node with low degree but high betweenness might indicate, definitely, it will indicate a bridge between two different cluster and a context specific synonym. Yeah, this can also be correct, because context specific, whenever we are talking about context specific, then it is a peripheral node, and when it is a peripheral node, then there is more chances of this high betweenness. Okay, so option A as well as option B. So a bridge between two different meaning cluster, a context specific synonym. Okay, so low degree, the word has few synonyms. High betweenness, it lies on the many shortest part between the words. This suggests a word links to semantic fields such as terms used in both technical and everyday context. Not a very frequent word, that is false. Not isolated. Okay, so this is also false. Isolated nodes have a low betweenness. Okay, so this is the thing. So option A as well as option B is the correct answer. Now let's move on to the last question of this case. What type of network metric can help formal versus informal word usage pattern? Page rank, clustering with sociolect subgraphs, tree depth, and diameter of network. This we have discussed during our theory, right? During our theory to this case, that is clustering with sociolect subgraph. So formal and informal language often forms distinct subgraphs. Okay, example: slang versus the academic vocabulary. Measuring clustering within the sociolect specific subgraph reveals stylistic grouping. Page rank measures importance, not register. Tree depth and diameter are global structural metrics, not socio-linguistic indicators. Okay, so option B is the correct answer. That is clustering within the sociolect subgraph. Sociolect subgraph means like slang versus formal versus informal. Okay, so that is the thing. So that is regarding the end of the case 2. So let's move on to the next case, that is case 3. The web graph, the structure of the web is modeled as a directed graph. Okay, so very necessary. Now this is a directed graph. Your synonymy network is also undirected graph, and your first network, that is the ingredient network, is also a undirected graph, but this web graph is a directed graph. Okay, so where nodes are web pages and edges represents the hyperlinks. Researchers analyzing the web graph discovered that certain sites like Wikipedia and government portals have high page rank. Okay, while some newer sites have lower visibility. Okay, so what you need to know about this case 3. So web as a directed graph. Okay, nodes will be web pages, directed edges will be hyperlinks, nature of the graph will be directed, large scale real world network. Okay, core concept, all this thing in degree, out degree. Now it is not degree. Okay, degree will be only in undirected graph, but whenever you will have a directed graph, you will be two type of degree, in degree as well as out degree. Okay, path, component as well as connectivity. Okay, page rank, it is very important. So a link based ranking algorithm measures importance of the web pages, that is page rank. Okay, key principle, number of incoming links as well as quality of the linking page, these two are important for this page rank. Okay, again I am repeating, number of incoming links as well as quality of linking pages. Okay, so the like A is directed to B. Okay, so is A important or not, that will also help to get the page rank of B. Okay, so that is quality of
Sir,
the.
how do they measure quality?
Quality means quality can be anything, like for different networks you can have different quality measures. For like social media, you can have different, like the number of times you are visiting the network, by that your quality is determined in any social networks. Okay, like this different network will have different measure of quality. Okay, generally social network links, like your Facebook, etc., all the social network you are using, the quality will be determined by how much time you are spending on that network. More time you are spending, the more will be the quality. Means quality means you will interact more with the network, right? So you will be more busy and you will have quality. So your node quality will be better than somebody else who is using less. Okay, so that is the quality in case of your most social networks. Okay, it can be different in case of other networks. So this is a common thing. Then role of damping factor, link weight distribution, just forget this interpretation. Many low quality links, modest rank, few high quality links, high rank. Okay, so dangling nodes, etc. Last class also we have discussed what is a dangling node: page with no outgoing links, that is dangling nodes. Why it matters? It can trap the page rank. It can trap the page rank because number of incoming link will be zero for a dangling node, and then requires correction in algorithm. Okay, so that is dangling nodes, so we have discussed in the previous class also. Then graph algorithm and ranking methods. Page rank, ranking influential pages. BFS traversal, Dijkstra supports path, crucial minimum spanning time. So just forget this. Scale free network, web graph is a scale free. Few nodes have huge links: Wikipedia, Google, government portals. Most nodes have very low links. Okay, so degree distribution, it follows the power law. Okay, and then last, link optimization and SEO principles. Okay, so just forget all this. So let's move on to the question. It will be much clear to the questions. Okay, so I just give me 2 minutes break. Yeah, so page rank is influenced by number of incoming links, quality of linking pages, number of outgoing links, or number of total users. So any guesses? I hope it is very clear cut. We have just discussed page rank is influenced by number of incoming links as well as quality of linking pages. Okay, so option A as well as option B is a correct answer. Okay, so this is the thing. So number of incoming links, quality, page rank of linking pages. Okay, page rank measures the importance of page based on link pointing to it. Not all links are equal. Links from high page rank pages contribute more. Okay, so number of outgoing links on the target page is accounted for in the distributing page rank but does not directly increase the page rank. Number of users traffic is irrelevant to page rank, it is purely link structure based. Okay, so that is the thing. So option A as well as option B is the correct answer. Now let's move on to the next question, that is that is question number 14. A page with many incoming links from low ranked pages is likely to have a very high page rank, never rank at all, have modest page rank depending on the damping factor, breaking the algorithm. Page with many incoming links from low ranked pages is likely to, so one factor is satisfying, that is it is incoming, it has many incoming links. Okay, but second factor, that is not satisfied, that it has low rank pages, that means low quality pages over here. Okay, so have very high page rank, that is definitely false, because one factor is satisfying, other is not satisfying. Never rank at all, that is also fault. But we can say have modest page rank, because one is satisfying, that is incoming links are more, but low rank pages, so have modest page rank, that we can say break the algorithm. So no, it will not break the algorithm. Breaking algorithm will happen only in the dangling nodes. Okay, not in this case. So option C is the correct answer. Okay, have the modest page rank depending on the damping factor. Page rank is weighted links from low importance pages at title. Even if low rank pages link to it, the total page rank may remain modest. It won't automatically become very high. It does not break the algorithm. Damping factor ensures stability. Okay, so option C is
Sir, what is damping factor?
damping factor. Whenever we are will be discussing about page rank, so there the formulas and etc will be given to you. Okay, so till now nothing has been discussed in detail, so only this social media datasets is we are discussing. So yeah, whenever we will go towards this dev section, so there we can discuss all this page rank in detail and this damping factor and all. Okay, so till now you just familiar with the term, and whenever we will be discussing that, we will say all these formulas and all this. Okay, so that will be clear to you all. Okay, so let's discuss the question number 15. Which graph algorithm is most appropriate to identify top influencers in web graph? Dijkstra algorithm, page rank, option C BFS, option D Kruxel algorithm. So again, that very simple, as this is a page rank case, so definitely page rank will be your answer, right? Which graph algorithm is most appropriate to identify top influencers in the web graph? So yeah, definitely the page rank over here, because web graph you top influencer will be identified by this page rank. Page rank ranks the nodes based on incoming links, structure and influence propagation. Dijkstra algorithm finds the shortest path irrelevant here. Okay, so that is the Dijkstra algorithm. It finds the shortest path. Okay, so that is not relevant. BFS is explore reachability, not importance. That if a node can reach another node or not. That, so that is BFS. And then you have your Kruxel algorithm. It finds minimum spanning trees, not applicable to directed graph. Okay, so option B is your correct answer. Question number 16. In the web graph, a dangling node is node with no outgoing links, a node with no incoming links, a broken hyperlink, and option D, a self looped node. So this also you'll also know. In the web graph, a dangling node is node with no outgoing links. So option A is the correct answer. A dangling node is a page that does not link to any other page, which trap the page rank in naive computation, because page rank it is always related to links. Okay, so no incoming links, simply a low ranked or isolated page. A broken hyperlink refers to dead links. Uh, Self looped node, a node linking to itself, not the same dangling. Okay, So this is the option A is your correct answer. Now let's move to the question number 17. Which of these changes could improve a site's page rank? Getting linked from authoritative website, reducing number of outbounds linked on important pages, removing the internal links, adding self-to. So any guesses for this? So yeah, getting link from authoritative website, so it will improve its quality. So definitely option A is right. Reducing number of outbound links on the important pages, so that can also be, yeah, that is also right. So links from high page rank sites increases your rank. Fewer outbound links on a page concentrates page rank, passing more weight to each linked pages. Okay, so removing internal link is generally harmful. Internal links help page rank distribution. Adding self loop does not increase page rank significantly. So this is the option A as well as option B. Question number
Can we
18.
discuss that it's dependent on quality and input, right? But here it's saying output. I didn't get.
Reducing number of outbound links, so outbound links, so fewer outbound links on a page concentrated page rank, passing more weight to each linked pages. So when there will be no outbound, so what will happen, no outbound, not no outbound, but reducing the number of outbounds, right? So when there will be less outbounds, it will pass its rank or pass its value to less important pages. Okay, means less number of pages. So that is why it is true, reducing number of outbound links on important pages. So fewer outbound links on page concentrate its page rank, means it will preserve its quality to itself. By that you can understand, passing more weight to each linked pages. Okay, so that is the thing. Okay, so again, page rank, I think the theory should be given to you as quickly as possible, so by that you can understand the better. Okay, so this is question number 17. I hope that page rank will be discussed sooner. Okay, so by that you can get more details of it. Okay, option A as well as option B is the correct answer. The web graph most resembles the undirected graph, balanced binary tree, bipartite graph, directed scale free network. So that you know this, web graph mostly resemble undirected graph, balanced binary tree, bipartite graph, directed scale free network. So option D is the correct answer, right? So yeah, directed scale free network. Web is highly heterogeneous. Few pages have many links. Mostly pages have few. Okay, this follows a power law distribution, typical scale free network. Okay, so undirected graph, hyperlinks are directional. uh, Balanced binary tree, unrealistic structure of the web. Binary tree means this hierarchy. Okay, so that is also does not follow in this web graph. And then bipartite graph, not applicable. All nodes are web pages, not two distinct types. So option D is the correct answer over here. So this is the end of your case 3. Okay, now let's move on to the case 4, that is social network dataset analysis using the graphs. So you are working with dataset of social platform. Each user is a node and edges represents friend connection. Using Python network X, you aim to understand central influencer, isolate clicks, and simulate potential viral content spread. Okay, so that you have to do. So theory is required: graph modeling of social network, nodes user, edges friend connection, graph type undirected graph because mutual friendship exists. Okay, so core concept: nodes, edges, degree, path, components of graphs. So network centrality measures degree centrality, betweenness centrality, closeness, and eagerness centrality. Okay, so degree centrality measures popularity, identify bridge between the community, that is betweenness centrality and closeness, and eagerness centrality influence the spread, structural importance. Okay, so community detection and click identification. What is community detection? Meaning of social circles, cliques, uh, 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 algorithm. There are different algorithm, again no need to discuss this. Degree of degree distribution and power law networks. The student may understand degree distribution, histogram visualization, meaning of distribution, shape, power law distribution, presence of hubs, scale free network concepts. So again, this is purely based on your visualization. And then data visualization histogram for degree distribution. Histogram means a node is connected to how many number of nodes. So by that we can form a histogram. Then rules of plots and network interpretation. Python tool network X and pandas. Okay, network X for graph creation, centrality computation, and community detection. Pandas data loading and pre-process. So this is the thing. So this is related to complete visualization of your social media network. So which Python libraries are best suited for analyzing such social networks? Network X, pandas for data processing, TensorFlow, and Seaborn. Okay, so any guesses for this? Very easy, right? Network X and
ABC,
pandas.
ABD.
Hello, has anyone asked anything? Okay. So network X and pandas, right? So these are the two things. Which Python library best suit? Network X and pandas for data pre-processing. Okay. So pandas, we first use pandas for data processing, and after that we can use the network X. So network X is a specialized library for graph creation, manipulation, and analysis. It provides function for centrality, community detection, shortest path, etc. Pandas useful to load, clean, and pre-process social network data before converting it to a graph. TensorFlow, it is used for machine learning. Seaborn, it is used for plotting only. Okay, not for network computation. So these are the
Sir,
libraries of.
we use matplotlib for plotting. Similarly, can't we use Seaborn?
Yeah. Very similar. Seaborn is very similar, but matplotlib is you can say there are more plotting option in matplotlib. Okay, than Seaborn. Seaborn will have all your this heat curves, etc., etc. So Seaborn might look beautiful, but matplotlib has all your graphs. So all your 2D, 3D, any plot, scatter plot, line plot, all the plot is matplotlib. Okay, Seaborn, it also used for plotting. It also gives good plots, but it does not have so many plotting options like your matplotlib. So always prefer your matplotlib over the Seaborn. Okay, so you can just explore the Seaborn also if you want. Okay, so this is the thing. So this option A as well as option B is the correct answer. So what metrics would best identify a user who connects disparate groups? So closeness centrality, betweenness centrality, degree centrality, or eigenvector centrality. Okay. So any guesses for this? Would best identify a user who connect disparate group means very separated kind of group. So closeness centrality is not will not be good because it is used for this within the cluster, but we want between the cluster. Okay, so connect two different clusters. So betweenness centrality would be good. Degree centrality, it is for all over nodes, so that is why we cannot say this. And last is eigenvector centrality. Okay, so eigenvector centrality, it is based on the importance of nodes, based on it is a centrality measure based on the importance of nodes. Okay, so again we cannot say that. So option B is the correct answer over here. Okay, so let's see. Yeah, betweenness centrality, how often a node lies on shortest path between other nodes. Users with high betweenness act as bridge, okay, between the different friends, groups, or community. Degree centrality, it counts connections but not bridging. Closeness centrality, it measures average distance to all nodes, does not capture bridging. Eigenvector centrality, identify the connected of influential nodes or important nodes. Okay, not the necessarily bridges. So option B is the correct answer. Now let's move on to the next question. Community detection can help identify social circle, predict content spread boundaries, compute path length, rank friends. So any guesses for this? Yeah, identify social circle should be true, and predict content spread boundaries. Okay, so this two must be is true. Predict the content spread boundaries. Yeah, this can also be true. So option A as well as option B. Yeah, community detection groups densely connected nodes into communities or social circles. This cluster often define the boundaries for viral content spread because information spread more easily within the communities. Okay, so computing path lengths is done with shortest path algorithm. So this is does not make any sense. Ranking friend is not primarily purpose of a community detection. So this to identify social circle, predict content spread boundaries. Okay, so option A as well as option B is your correct answer. Okay, so this is the thing regarding this question. Okay. So let's move on to the next question. A tight knit group of users with many mutual friends is likely to form a page rank cluster, a path component, a community, a bipartite set. So very easy. Tight knit group means community. Okay, a community. So option C is the correct answer. Social network, a community, a set of nodes with many internal edges, relatives to edge outside the group. Okay, so many internal edges relative to edge outside the group, that is community. Okay, page rank cluster is not a standard term. Path component refers to connected components, and bipartite set requires two distinct nodes type, not the case here. So option C is the correct answer. Okay, so let's move on to the next question. Which of these plots would helpful in visualizing the degree distribution? Option A histogram, option B uh, log plot, option C heat map, option D confusion matrix. Which of these plots would help visualizing the degree distribution? So any guesses for this? It's very easy. Histogram should be there. Yeah, histogram shows the frequency of nodes having each degree. Okay, so each degree how many nodes are there for each degree, so that the histogram shows. Okay, so this is the standard and most straightforward way to visualize degree distribution in social network. Log plot is not necessary unless specifically analyzing power law scaling. It is used for fitting or confirming heavy tailed distribution, but not for basic visualization. Heat map, that is again popular, but it visualize matrices or correlation, not degree counts. Confusion matrix are for this classification prediction task. Okay, so just forget about that. So option A histogram is the correct answer. Let's move on to the next question. Which What does a power law distribution in degree typically suggest? Uniform connectivity, presence of hub, graph is bipartite, and random structure. So just see this presence of hub, it determines. Okay, power law distribution. Power law distribution it's heavily tailed, few nodes have many connection, hubs most have a few. So that is power law degree distribution. Okay, heavy tailed, few nodes will have many connection, most have few. Okay, so that is why power law distribution in degree typically suggests this presence of hub. Okay, uniform connectivity would be flat distribution, bipartite structure, unrelated. Random graphs often follow Poisson distribution, not a power law. Okay, so option B is the correct answer, that is presence of hub. Now let's move on to the case fifth, or the emergence of connectedness. As a new mobile messaging app gains popularity, its user network grows. Initially users are isolated, but as invitation spreads and group chats are created, a giant connected component emerges. Okay, so that is emergence of connectedness. Researchers study when this happens and how rapidly such transition occurs. Okay, so this is the thing about emergence of connectedness. Okay, so yeah, so random graph models. So random graph model I have already discussed. Okay, then phase transition network we have discussed, percolation theory we have discussed, we have discussed giant connected component, critical threshold, this is the probability. Okay, pc 1 by n. Okay, this also we have discussed connected components in graph, and network growth and connectivity matrix. So role of average degree, network size, network diameter change, and component size evaluation. Okay, so these are the things. So most of the things we have discussed. So let's see the question, it would be good. Question number 25. The sudden emergence of giant connected component is an example of phase transition network, percolation theory in action. clique formation or graph diameter reduction. So graph diameter reduction is definitely false because graph diameter will increase, not decrease. Clique formation would not, also does not make sense. Okay, clique formation means small cluster, so that is clique, so that is also false. So phase transition in network, that is true, and percolation theory in action. Okay, by this only this emergence of connectedness happens. Okay, so option A as well as option B is the correct answer over here. Okay, so as our random edges are added to the sparse network, isolated cluster suddenly coalesces into a giant connected component. This is analogous to phase transition in physics. Percolation theory studies this phenomena formally, modeling connectivity threshold in networks. Okay, clique formations, small fully connected groups, small cluster, I have told you, not the global giant component. Graph diameter reduction may occur, but uh, a consequence, not a fundamental phenomenon. So I don't think graph diameter reduction will also happen, because the this large connected graph will be formed, right? So how it will happen? So this is not also false. So option A as well as option B is the correct answer. As new edges are added randomly, when is a giant component most likely to emerge? After adding 10% of edges near the critical threshold in ER model, and then immediately when all nodes have the same degree. So again I am repeating, as new edges are added randomly, when is a giant component most likely emerge? Okay, so near the critical threshold in the ER network, that will be correct, right? Because when the near the critical threshold, your k value will approximately approaches to 1, and in that one or the critical threshold, and then a giant component most likely to emerge. Okay, so this is the concept. After adding 10% of nodes, arbitrary the threshold depends on n. Okay, immediately initially the network is too sparse, so immediately won't happen. When all nodes have the same degree, not necessarily, randomness drives the phase transition. So the option D is also false. So it is very straightforward, near the critical threshold in the ER model. So option B is the correct answer. Then factor influencing the rate of connectedness emergence include average degree, number of nodes, time of the day, or the color of the nodes. So this is also very easy. Average degree, that is correct, and number of nodes. Okay, so this two will influence, actually, number of nodes and the probability. Okay, probability of linking. So probability of linking is also associated with the average degree. So that is why average degree determines how many edges a node has. More edges accelerate the connectivity. Okay, so the P, there are two things, right? P and N is the number of nodes and P is the probability of linking. Okay, so this many edges, if we will have many nodes with many edges, that is increase the average degree. Okay, it determines how many edges nodes has. More edges accelerate connectivity. So more number of average degree, more edges will accelerate the connectivity, right? So we have seen like 25 into 25 friends in a cluster, right? So if you just increase the number of nodes, what will happen? The number of connection will also increase. Okay, so that is why average degree, when you will increase, what will happen is average degree will increase, means you will just you can say you will uh, just increase the size of the cluster. Okay, so when you will increase the size of the cluster, what will happen is more number of connections, so that is why your P will increase, and number of nodes increase, your N will increase. When P and N will increase, what will happen? The rate of connectedness will emerge. Okay, so option C and D are the false answer. Okay, so option A and B are the correct answers. So question number 28, which real world phenomena reflects the same principle? Okay, so a virus mutating, trending hashtag, a viral video suddenly reaching millions, blockchain mining. So which real world phenomena reflects the same phenomenon? Virus mutating, A trending hashtag, a video, viral video suddenly reaching millions. So option A, B, C should be right according to me. Okay, option C is only given. Why not this? Virus mutating, biological change, not connectivity. Okay, and trending hashtag similar, but the viral video better capture the mass connectivity. So I think trending hashtag should also be true. Okay, so option A is right, and according to me, option B should also be right. Okay, sorry, option B and option C should be right. Okay, no, option A I cannot say because virus mutating, it is a biological change, not connectivity. But then when you have this virus like COVID and also that, in that case it is actually true. Okay, so option C should be definitely right, and option B I think it is right. Okay, so B and C should be right according to my opinion. Okay, option A, yeah, there can be doubt because that virus is mutating, but that virus is spreading or not, that we cannot say. Okay, but option B and C according to me is should be true. Okay, so this is the thing. Then yeah, option D, blockchain mining consensus mechanism unrelated to emergence of, yeah, giant components. So blockchain mining, that is different. Okay, so that is different. So option B and C according to me is the correct answer over here. Okay, so this is the now. Okay, someone is joining. Yeah, which of this method can detect when a giant component has formed? Analyzing component size over time. Okay, just 1 minute. Yeah. Analyzing component size over time, checking network diameter, BFS from random nodes, and comparing node colors. So option D should be definitely be wrong. Option D, BFS from random node also, yeah, it is transversal. So which of this method can detect when a giant component has emerged? It can be, but I cannot say. Checking the network diameter, definitely according to me, and analyzing component sizes over time. Yeah, component sizes mean cluster sizes over time. So if cluster size will deepen, according to me, that is also true. So option A as well as option B. Yeah. So analyzing component size over time. So analyzing component size over time, the most direct method, you can track the size of all the connected components and edges are added. When one component suddenly contains a large fraction of nodes, the giant component has emerged. Okay, so that is why analyzing component size over time. Checking the network diameter, longest shortest path between two nodes is in the largest component, changes noticeably as a giant component forms. Initially, the network is fragmented. After the giant component connectedness, after the so initially the network fragmented, so diameter of the largest component is small. After the giant component emerges, diameter suddenly jumps and trend stabilizes as more edges connect the nodes. Therefore, monitoring diameter can also indirectly indicate the giant component formation. BFS from the random node might miss disconnected components, not reliable for detecting global giant component. Okay, yeah. So it might miss the disconnected component, so that is why it is false, and definitely last is false, unrelated. Okay, so option A as well as option B is the correct answer. Now let's move to the question number 30. Okay, question number 30. In a graph theory, the component is central node, directed edge, maximal connected subgraph, a subgraph with cycles only. So it should be maximal connected subgraphs. Yeah, maximal connected subgraph. A component is a subgraph where every node is reachable from every other node, and adding any other node would break this property. So that is why it is known as subgraph. Okay, central node, the single node is not a component. Directed edges, just one link, not a connected subgraph. Subgraph with cycles only. Component can be acyclic as well. Okay, so that is why option C is the correct answer. That is a maximal connected subgraph. Okay, so this is the thing. So this ends our case number 5. Now we have this last case, that is the case number 6, online learning, collaboration and influence. So in online learning platform, users interact by asking, answering questions, collaborating on the assignments, and sharing resources. Each user is a node. Interactions such as replies, comments, or co-enrollments are edges. Analysts are interested in understanding influence dynamics, collaborative learning patterns, and knowledge diffusion. Okay, so the theory that is required: graph model of online learning platform. So nodes, users, edges, all these things, replies, comments, collaboration, etc. Graph types: directed graph, replies, comments, that was directed, yeah. Undirected graph: co-enrollment or collaboration, that can be uh, undirected. Okay, so core concept, these are the all this concept. Centrality measures, again you have all this centrality. Okay, we have discussed again and again. In degree, centrality measures popularity and attention received. Identify influencer contributors. Option B, eigen value centrality measures the influence based on connection to influence user. Betweenness centrality identify bridges between learning communities. And closeness centrality measures spread, speed of information spread. Okay, now we have this clustering coefficient relationship to tightly knit learning groups, collaborative circles, community detection algorithm. All this algorithm is there for community detection. Tie strength and collaboration, meaning of strong ties, how repeated interaction builds trust, collaboration. The examples like peer feedback, repeated co-participation, knowledge diffusion, and information spread. How information flows in a network: closeness centrality and betweenness centrality. These are the two important centrality for the knowledge diffusion. Okay. So question number 31. Which of the following network properties would best identify influencer contribution? High in degree, number of incoming replies, comment. High eigenvector is centrality. Low clustering coefficient, and membership in isolated components. So option A as well as option B, right? Yeah, so option A as well as option B: high in degree, that is number of incoming replies, and high eigenvector similarity. So high in degree: users receiving many replies or comments recognized by peers, indicating influence. High eigenvector similarity, centrality, being connected to other influential users, increase a node's overall influential score. Low clustering coefficient, definitely it is wrong, so does not include indicate influence. It measures how interconnected neighbors are, so this does not make any sense. Membership in isolated components means the user is disconnected from the main network, unlikely to be influential. Okay, so this is also wrong. So option A as well as option B is the correct answer. So let's move on to the question number 32. Which metric would help detect tightly knit learning groups? Degree centrality, clustering coefficient, C page rank, and D H betweenness. So definitely the clustering coefficient, right? Yeah, clustering coefficient measures how interconnected a node neighbors are. So high clustering indicates user participate in densely tightly knit study or discussion group. This degree centrality counts the connection but does not capture group cohesiveness. Page rank, it influences rank, not tightness of the group. Edge betweenness identify bridges, not dense clusters. So option B is the correct answer. Let's move to the question number 33. So a user with high betweenness centrality is likely to connect different learning communities, facilitate knowledge transfer between the group, be isolated from code discussion, have the most followers. High betweenness centrality, so high betweenness centrality collect different learning groups, facilitate knowledge transfer between the groups. So option A as well as, again option A as well as option B should be the correct answer. Isolated from the code discussion, we cannot say. Have most follow, we cannot say. Okay. So high betweenness centrality means user lies on many shortest path between other users, such as user bridge communities, transferring knowledge across otherwise separate groups. Okay, they are not isolated, they are centrally structurally centered, having the most followers correspond to degree, not betweenness. Okay, so option A as well as option B is your correct answer. Question number 34: which algorithm is most suitable for identifying natural study groups in the network? BFS, Dastra, community detection, or Kuxel algorithm. So this is community detection. Okay, so community detection, yeah, community detection finds cluster or densely connected node represents natural study group. Okay, so definitely identifying natural study groups means we have to detect the community. Okay, so that is why option C is the correct answer. So BFS, it explores reachability, not cluster. Dijkstra, find the shortest path. Quixel algorithm, it builds the minimum spanning trees unrelated to communities. Okay, so this is the question number 34. Question number 35: factors contributing to strong collaborative ties may include frequent co-participation in thread, repeated peer review or feedback, random logins, or D, the degree of anonymity. Factors contributing to strong collaborative ties may include frequent co-participation in threads. Okay, repeated peer review or feedback. Yeah, the option B should be right. Frequent co-participation in thread. This can be right. Random logins, we cannot say degree of anonymity. So again, I think option A as well as B. Yeah. So frequent co-participation in threads as well as repeated peer review or feedback. So strong ties arises from repeated meaningful interaction. Okay, random logins that don't create meaningful collaboration. Degree or anonymity may reduce tie strength rather than contribute it to it. Okay, so option A as well as option B. And let's move on to the last question. Okay, in such a learning network, a node with high closeness centrality can disseminate information quickly to the whole network. Okay, high closeness centrality. Okay, only influences direct neighbors, be easily removed without effect, belong to disconnect components. So uh, disseminate information quickly to the whole network. Okay, so such a learning a node with the high closeness centrality. Okay, only influences direct neighbors. It might look true, but we cannot say only influence. Okay, so that is why I think it is false. Easily removed without effect, belong to disconnected components. We cannot say so. Only influences direct neighbors. That can be right, cannot be right. But option A, yeah, okay. So closeness centrality measures average distance from a node to all others. Okay. So that is why nodes with high closeness can effectively reach the entire network with idea of spreading knowledge. It is not limited to direct neighbors. Yeah. So such nodes are not easily removed without effect. They are critical. Disconnected component reduce closeness, so many closeness nodes must be in the main connected network. So option A is the correct answer. So by this we have ended our 6 cases for this discussion session of week 2. Okay, so this is regarding the discussion. Okay, so I know it is all theory and theory, but I cannot do anything. The subject is mostly like that. Okay, so before going and let me just show you some of the codes that will help you.
Sir, will we get the recording?
Yeah, that YouTube video link I have shared na, in that video link only, if you just open the video link, that is week 1 discussion, that channel you just subscribe, and you can get the video whenever I
Oh.
will be
For
uploading.
week one, we got a mail, sir. With that, we can get, no? In that only.
Yeah, so for all the weeks only, for all the weeks you will get the your video in the same YouTube channel. Okay, so that is
Okay.
what I am saying. So you can just subscribe the YouTube channel, so you can get without any problem. Otherwise, the master link also I have shared. In that master link also, this is very important. So that master link also, whenever you will open, you will get recording of all your
Sir, can you please reshare it? I joined late.
okay. So this is the master link. Okay, so this is the master link, so you can just
Thank you.
go, and this is the drive link where I will be uploading all the slides and codes. Okay, this is the drive link where I will be uploading all the codes, and this is the YouTube video link of the first class. Okay, so just open this video link and you will get link of the you can subscribe that channel. In that channel I will be uploading all the videos. Okay, so these are the three links. So just let me show you some of the codes, so that will at least interest you. So yeah, so social network analysis using network X we have done. So supports all this files: CSV, edgeless, GML, .NET, GraphML, GXF, dataset, Facebook, Karate Club, and other real world datasets. So what is social network dataset? I have given V is the set of nodes and E is the set of edges. Okay, scripts perform graph loading, visualization, degree distribution, density, clustering coefficient, diameter, etc. Okay, so what we have done, we have just imported all the library, that is network X, pandas, matplotlib, and then collection, a library called collection. So we have import counter. Okay, so these are the libraries, and then what we have done, we have Network X provides several built-in graph generators and example dataset. Okay, some are Karate Club graph, Florentine families, diverse Southern women, less miserables, random graphs, what's all this datasets. Okay, so from all this dataset, we will be using this Karate Club graph loaded. Okay, so how to load the dataset? Just write this annex.karate club graph. By this, what you will done, you will load the karate club dataset. Okay, so once you load the karate club dataset, function to load different type of dataset. So you can see the function to load different type of dataset. If so this is a built-in dataset in your network X, so you can just call out. But if you are just downloading the dataset and uploading it to Colab, then you have to for seeing the dataset you have to load like this and then return like this. Okay, so this is how you have to do it, and then we will create a graph object using this. So this is a directed graph, so this is how our graph has been created. Okay, and then degree formula, this is the degree formula, number of edges connected to node V. Okay, so we have seen that 0 degree, 16 nodes have 0 degree, 9 nodes have 1 degree, 2 nodes have 10 degree, like that. Okay, so this is unique degrees. So count of each degree, number of nodes with degree k. So if we want to see number of nodes with degree k, so that also we can count. So degree counter, 2 nodes has 11 degree, 3 nodes has 6 degree, like that. Okay, so this is the thing, degree counts. Yeah, so first is the degree count and second is that thing. Okay, second is the second is the number of nodes. Okay, so degree count 2, 11 nodes are there, degree count 3, 6 nodes are there, degree count 4, 6 nodes are there, like that. Okay, so this is the distribution plot or histogram that we were talking about. Okay, so this is the distribution plot, so you can see degree and number of nodes. For example, let's say this is the number 1 degree, so for number 1 degree you have number of nodes equals to 1. Number 2 degree you have like 11 number of nodes, like that. Okay, so this is the degree and the number of nodes. This is the plot degree distribution line. So this is how we have plot the degree distribution line. Okay, number of nodes and degrees. Okay, so this is the thing. Then zoom degree distribution, just zoom out this curves so we can see this. Okay, so for example, we just want to see from degree number 1 to 10 only, so we can zoom the degree distribution. Okay, and then network density, this is the formula of network density. So by this we can just pass out this density and we can get the network density. Okay, and then local clustering node, that is also a formula, clustering dict. Okay, by that we can get the clustering dictionary. Okay, and average clustering coefficient. Okay, so average clustering coefficient by average clustering. Okay, and clustering dictionary by clustering dict. Okay, so these are the two things. So this is also nice. And then diameter of network. Okay, diameter maximum shortest path length. Okay, diameter 5 is coming. Okay, by this diameter. Okay, and then summary statistics function, like how many nodes, edges, density, cluster, average clustering, diameter, all at once. So just summarize all these things. And centrality measures are there, for example betweenness centrality, closeness centrality, eigenvector centrality. Okay, so that also we have calculated. Okay, so you can just see over here. Okay, so this is the thing. And then we have this community detection. So community detection by this given communities, so first level and then low one communities. So this is the another, these are the two different algorithm. One is given Newman algorithm and one is the Lowian method. Okay, so that also you just need to pass this. Okay, first level, and you, for this Lowian you have to pass this community Lowian. Okay, so you can just see this and you can check this. And then this power law fitting distribution, so that also just fitting a power law, so that is actually not so important. So this is the entire code. Okay, so you can just load the you can just open this code, and here something copy to drive would be written, and just press the copy to drive, and that code this code will be copied to your drive, and then you can run the code and also make changes according to your wishes. Okay, so this is the first code. And second, also I have done this emergence of correctedness. You can just see over here. So I did not have much time, so that is why I have done everything in a single bar. Okay, so just you can see that how by adding nodes and edges, how our component giant component ratio is increasing. Okay, 882 we have this component ratio 0.039, but when we have increased the edges from 882 to 88234, our component ratio, rather 85221, our component ratio reaches 1. Okay, so this is emergence of correctedness. Again, you can just see this code. What these are the steps: import and libraries, load edge list, extract unique nodes, and then shuffle edges randomly, prepare fraction of edges, incremental network is construction. That is, we have to increment the either nodes or either edges. Here we have increment the edges. Okay, so this is the thing. And then visualization and all this. Okay, so you can just see over there. So this is the graph. You can see giant component ratio, it was 0.034, right? 0.039. Okay, 0.039, 0.039 with 882 edges. But when we increase the edges to 85221, our component ratio giant component ratio almost reaches 1. Okay, so this is emergence of connectedness in your Facebook network. Okay, so this also I have given to you. Okay, so just check this and it will be fun. These are the two codes. So with this I am ending the session for today. Okay, thanks for joining, and we will meet on the next Tuesday, same time, 6 to 8 p.m. Okay.
Thank you.